Good evening, folks. Hope everyone is okay. So, in the last talk, we have been talking, or we started talking about internet data science, and we started talking about internet data science in the context of the entities that actually help in terms of facilitating, just, watching a movie, right? Which was our motivating example. And we kind of teased out all the different entities that work in the background. And, the slide here kind of shows all the entities that, actually work together and kind of exchange information with each other so that, somebody like, you and I can watch a movie, right? And this is not just for movie, but for any application like remote learning, for example. This Zoom call is a good example of that, right? And we kind of went into each one of these individual pieces in terms of what these entities are composed of, and kind of like, went into what the core notion of internet data science is all about, right? So all these entities do exist, but the key questions that pertains to something like internet data science is answering something like, is there some information about these entities at all? Do we even know these relationships exist? If so, what is the data set available for them? And do we understand the data enough in terms of quality, meaning how good are they? Is there any bias in the data? Or, if you, look at the data, do you have a representative coverage? Meaning, are you covering all the locations, all the users, all the services? And how stale is the data, right? Meaning, is this taken recently, or is this taken like last year or 5 years ago? And what about some of the properties, right? And if you don't have any of the data set for meaningful relationships, then you basically infer what the data can do, right? So, we kind of looked into this in terms of relationship, and we said, this is a super complex picture. And, we showed a couple of examples in terms of the relationships itself, in terms of what constitutes the relationship between the entities. And so we kind of stopped here with this particular story where one entity relationship is, IP geolocation, and this is something a company like MaxMind always does. So you enter your IP address, and you get the geolocation back, which means you can associate two entities together based on the data set that you have from MaxMind. Now, a whole bunch of questions arise, right? So the relationships are there, the data set exists. Now, what about the quality, coverage, validity, and invariant properties? So let's look into that, and let's start from here. But before proceeding any further, do we have any questions in the room about what we looked at in the previous talk versus where we are going to go now? All right. So the answer to this particular question is, okay, do we know everything about the relationship between IP addresses and geography? Is a straightforward no. And if you recall, we kind of like stopped at the story in the last one as well. So if you think about what IP geolocation can do for you anytime you are looking at a particular product, or there's all the targeted advertisement, customized searching, and everything is powered by IP geolocation, right? But unfortunately, this information is not complete, and this is not always valid, and the quality of the information that you have is like really, really bad. So one example to illustrate the badness of the information is this particular story. So there was a farmhouse in Kansas, and there was this old couple, and this old couple were always harassed by FBI agents, marshals, tax collectors, police officers for all sorts of problems, right? And even their information was like, scraped and, posted in all sorts of websites, calling them fraudsters. But apparently, they were really nice people, right? And the key culprit that kind of pinned them and made them go through all these issues, it's not actually their job, or it's not what they did. It's basically the quality of IP geolocation, right? Anytime the information is stale, or if the information is not completely available, it's just going to give the geographic center of the country. So in this case, it's going to just point to a place in Kansas, which is the center, right? And apparently, this couple, kind of lives very closer to that geographic location. So anytime when all these agents are using an application to figure out an address, and come up with a location, essentially this house always shows up, and these agents always show up at the house and ask all the questions, and rest is kind of history. So this is a good example of how bad a quality can affect some of the applications. Again, remember, we are just talking about one entity relationship between IP address and geography. Now, if you imagine a bigger question, right? How large is a internet service provider in a particular country, right? Or you want to ask this question in terms of the number of customers that are served by this ISP, then you just have to associate so many entities together, right? In this case, if you want to reason about the number of customers, you need to know, how many users are allocated with IP addresses, where are the organizations which are mapped to autonomous systems and logical topology that are using the service, right? If you're using Vodafone's mobile service, you're probably using a whole bunch of their logical topology as well as autonomous systems where they exchange traffic with one another. So just to figure out how many users are using the internet in a particular location, you just have to piece out so many things. Now bring back the previous anecdote. What if this is incomplete, or what if this is incomplete or unknown, or what if some of the arrows here have errors, right? It is a magnitude of error that's going to be introduced in the inference, and of course the inference will have a margin of error that needs to be accounted. Again, this is a example that builds on top of the previous case. Now think about a even bigger example, right? How large is an ISP in a country? Think of a country like India, and think of Reliance, right? Now if you want to map the footprint of a particular service provider in a country like India, now we have to put multiple pieces together and multiple data sets together, and then try to reason about their association and relationship with each other. And this is not just the end story, right? So even though you put all the pieces together and try to answer a question, there are certain things that you still don't know about what's going on in the internet, right? For example, providers are rolling out new types of technology every time, right? One example is think of Google or AWS or Azure, right? These cloud providers, they always roll out a new type of connectivity called virtual private interconnection. So even when you don't have a autonomous system number, you can still be connected to the internet, right? And you can still use their services. And from an external perspective, nobody even knows who you are, right? Same is the case with Tor, right? It employs this technique called onion routing, and only up to so many hops you will be visible. Beyond that, nobody knows who you are, right? And same is the case with VPN. Your geography is always hidden because your location is bounced off elsewhere. And inferring the relationship in terms of geography to IP addresses as well as logical topology is really hard. So even though you want to reason about some of the grand questions in the internet, you just don't know enough information about some of these relationships and the entities involved. Another key challenge, in addition to this issue of unknown relationships, is the fact that some of them will have errors. Right? End of the day, the data set is either collected by researchers like me, or it is given by providers like AT&T's and Reliance of the world, right? So they don't have to give everything, and I'm bound to make errors when I collect information. So which means that you have to take it with a pinch of salt, and not rely on the data as is. So the data will have some error, and you should always account for that when you try to create models out of these data sets. And finally, you overcome this issue of unknown nature of data as well as errors. But then there is this grand challenge of, okay, will this relationship change over time? And the key reason why we should even ask these questions is, because of multiple reasons. One, the technology always changes. You know, some time ago, it was all wired connectivity, and then became wireless, and then became, the mobile phones that we have today. Now it's all IoT and smart devices, right? So the technology has been changing over time. And the connectivity technology has also been changing. It was PSTN, and then copper cable, and then fiber. Now it's all, wireless, satellite, whatnot, right? And the ISPs, because of all sorts of cost issues, they also roll out new technology infrastructure into the internet, especially to manage their networks, because of which things change all the time. So because of these three factors at interplay, it's always hard to come up with a stable picture of what these relationships look like. And that's why, if you work in networking research, you ask a question today, you'll get one answer, and you ask the same question after 5 years, the answer will be completely different. All right. And you ask the question in one location, the answer will be different. You ask the same question in a different location, the answer will be completely different. So the internet in general is constantly changing. It's in a state of flux. And so, these questions are really key in terms of, making sense of these relationships. And that's, one of the fundamental tenets of internet data science. So, once you know the data, you just need to understand all these different properties. Okay, so before proceeding any further, I want to quickly pause and see if there are any questions in the room. All right. Okay. So we just said, there are all these unknowns, right? We don't know if things are stable. We don't know if there are errors, and we don't know if there is even a relationship between a bunch of these entities. Now, that is when this notion of inference comes in, right? You don't know something, but based on what you already know, can you infer, some of these properties, some of the phenomenon that happens in these relationships. And overall, right, once you know things exist, the data as well as the quality, and finally the inference part, all these are, part of the internet data science research area. So that's the main focus. So it's not like just developing machine learning models. There is a lot of data involved, right? When some of the data science folks really claim that, hey, we have been doing all the big data stuff for a while. They just have to look at other communities, especially database community as well as internet measurements community. We have been dealing with petabytes of data for a very long time. So this wave of ML and AI, yes, it is all there, it is all recent, but then this notion of statistical properties, studying some of the invariance and validity of the data, this has been the bread and butter of internet measurements research for a very long time now, at least for the last 20 years, and that's kind of fueling many of the companies like Akamai and some of these content providers. Okay, so given this high level overview of internet data science, what are some of the key issues, right? So we know, this data issue is there, but then let's say we want to, infer some of these relationships and infer some of the events of interest, infer some of these phenomenon in the internet. Now, what sort of issues might arise? And that's going to be the focus of the next couple of slides. So anytime when you think about, developing a bunch of models, again, I'm talking about all this, maybe, this is familiar to some of you. I'm talking about all this because, in the survey, some of you said you're not really comfortable with AI machine learning. I just want to incorporate some of the feedback so that, you are all on the same page. So anytime you want to incorporate, um, machine learning or AI aspects into any problem of interest, in this case, it's network management, right? You need to have ground truth. You need to have labeled data, right? Unless you have, this notion of a labeled data, you cannot even train a model, right? So you need to have good examples of what events of interest might look like. You should also have bad examples, and they should be balanced, right? It should not completely be good examples. It should not be completely be bad examples. Right? You have to have good balance of good and bad examples in the data. And that's, something very generic for any machine learning, AI modeling in general. But then let's be very specific with the context that we are talking, right? So we are talking about network management, and network management problems arise because of two things. One is a network attack, like a distributed denial of service. Recall, the first couple of projects that we spoke about. So DDoS is a major problem where a flood of traffic is sent into the network. Now, it's a very generic definition, right? A flood of traffic is sent into the network. Now, how would you concretely or, quantitatively define a DDoS attack for a particular network, right? Now, based on that definition, how would you create good examples and bad examples for DDoS, right? Only when you can do that, you will be able to develop machine learning models. Same is the case for network congestion, right? It can be because of a performance event. It can also be because of an attack. So when a congestion event happens, is it because of TCP or is it because of DDoS? If so, on which port, on which location, which application? You need to map out all these different things and be a bit more concrete, right? You cannot generically define what a network congestion is. And because of, these issues, coming up with this notion of labels for network events is completely, impossible, if not really hard, right? So in that sense, what can you do to, come up with labels? That's one of the key issues that, people working in this area always wrestle with. And how do you come up with, like, ways to label your data so that you can come up with, like, good, robust models? So that's the first issue. Any questions so far? All right. And the, issue of lack of labels is further complicated by the fact that the community is like kind of like distributed, right? There is no one size fits all agreement for the features using which, these problems could be detected or identified, right? So if you think about something like image processing, you can easily identify a cat because you know what a cat looks like. It always has whiskers. The eye features will be different. The ears will be different. Same is the case for dogs with, like, paws and whatnot. Um, but when it comes to DDoS, there are, a wide variety of attacks that are out there. When it comes to congestion, there are a wide variety of congestion events that can happen. Now, of all those different types of DDoS attacks and congestion events, how would you come up with like K common features for DDoS or N common features for congestion, right? That is another big issue. So this lack of labeling is just, getting complicated over and over because of this lack of agreement in the community as well. And this is even further compounded by the fact that the way people collect data is entirely piecemeal, meaning There is no one standard way to collect data, right? You collect data at different locations. Some of them collect at the core of the network, some of them collect at the border or the edge of the network. And those have different properties, right? Because edge is more aggregate, you see everything, whereas at the core you see specific traffic. So in terms of where you collect the data, the granularity of the data that you collect is entirely different. Um, and it's also the how, right? You can collect packets, which are singleton units. You can also collect flows, which are a group of packets with certain specific characteristic. You can also collect logs at the server, and all these will have different types of information. So the granularity is different, the type is different, and the usage is also different, right? We all work during the day, or at least try to work during the day, and sleep at night, unless you're a night owl. So depending on when the usage happens, the characteristics that you can apply or you can observe will be completely different, right? So the granularity is different, the type is different, and the characteristics are also different. And at what level are you collecting? Are you collecting at the network level? Are you collecting at the wire level? Which means you can get a whole bunch of packet level information at the network level. Or are you collecting at the application level, meaning you just have an app and you're trying to figure out something from the logs, right? Depending on at which level, the questions that could be answered are completely different. So because of this, right, at any point of time, let's say you're collecting data at the core, and the data collected is a flow, and you're only collecting at midnight, and the information is about a bunch of applications, right? Now that's a different piece of the pie, right? And you can do the same set of combinations for different of these approaches, and essentially you're left with a whole set of approaches that are out there, and each approach has its own set of pros and cons, right? And because of this fact alone, right, coming up with a labeling is even harder, right? So it's not just about bad examples and the availability and the definition of events as well as community agreement. It's also about the way networking works in terms of abstractions, and you're left with so much in terms of possible spaces to collect and manipulate data. And finally, even if you overcome all these different issues, right, there is always one thing that's going to triumph, and that's the privacy issue, right? Users will not be happy if they collect, if they are, part of the data collection process. And that's why all these companies are really smart, right? Google, for example, gives everything for free, and there was this nice documentary in Netflix. They really coined the phrase well, which is, if something is free, you are the product, right? So that's why they let you use everything for free so that they can use your information for their own business, right? So they collect all sorts of raw data. And before you sign up for the service, they'll give you this big form. None of us will read it. We'll just scroll, click OK, and there you go. You just sold your entire history of data to them, right? So there is all sorts of your private identifiable information that goes to companies like Google, and that's the same with networking as well. When people collect information at the packet level, they can even infer what's in the payload of the packet, like passwords, for example, unless the packets are encrypted. And there are all FERPA issues. Again, this is country specific. I'm talking about something in the US, but depending on which place you are at, you might have some variant of such issues in terms of collecting data. So you cannot just give raw data to people, and the sharing is frowned upon because of this. People came up with their own piecemeal approaches. So raw data is a big no. You cannot share with people when it comes to networking. Now, given that that is not possible, another option is, can you share the trained machine learning model? Let's say you collect the data, you do a whole bunch of processing, you do error correction and whatnot, make sure the data has no bias, and finally develop a model. Okay. Now, can you share the model? And the recent answer to that question is a big no, because researchers recently demonstrated what is called as the model inversion attacks, meaning you have a model, right? So you go from the data to the model. Now that model can be used to go back to the data. So just because you have a model which is considered to be a black box doesn't mean that it is, completely without any PII or any private information. So people can always use models and infer the data from it. And that's called a model inversion attack, by the way. So, this has been proven in, medical domain and all those things. And so, this sharing of machine learning models is always frowned upon because of those reasons. So you cannot share data, you cannot share machine learning models. You are left with a whole bunch of broken approaches. You don't have features, you don't have labels. Now, how can you make progress in this area? How can you share data? Right. So that's the key thing that some of the efforts are focusing at. So there are many piecemeal efforts again, but to me there are three really big efforts that are pushing this area out. The first one is from UC San Diego, and this group is called CADA. So what they have been doing is they have been collecting data sets about different facets of the internet, right? They have been looking at all these different piecemeal approaches for a while now, and they have put together a nice, archive of, data related to the internet. So if you're working on some networking problem, this is a super useful resource. They have good information there, and so that kind of like takes care of this problem, right? And then yours truly is actually working on all these other aspects of lack of data, how to create labels in an automated fashion without doing all the manual processing, and how to do privacy preserving collaboration, meaning you don't share the data, you don't share the machine learning models, but you just share what we call the labeling functions. Recall the previous talk. So we briefly spoke about labeling functions, which are programmatic representations of operators' domain knowledge, right? So that could be shared between different entities, and so that could facilitate collaboration, taking care of this issue as well as this issue. And then finally, there is also an effort by my friend and colleague Arpit from UC Santa Barbara. So he's been pushing this area of operationalizing stuff. Just because you develop a machine learning model for some of these data sets doesn't mean that you can just deploy them in the network, because it has to be absolutely crystal clear and fast, right? So that's another nice effort out there, and the link is given here. But in a nutshell, right, all these efforts are basically working towards this vision of a self-driving network, meaning you try to make the networks more smarter based on the data that you collect, decide what the data says, and take an action based on the decisions that you make. That's called a self-driving network. And this is very similar to this whole notion of a self-driving car, right? So many of you should be very familiar with a self-driving car. So this was like, back in the day, proposed by DARPA, which is the Defense Advanced Research Project Agency. And those guys are the ones who are, building all these big things. Internet is a byproduct of, their funding, basically. So they always come up with these grand challenges. One of the grand challenges they came up with back in 2004 is this notion of a self-driving car. Can you build something that can run on its own in the road by sensing the data about the road in terms of what is currently going on, is a pedestrian crossing, and whatnot, infer whether it's a pedestrian or is it, just a mirage, and then, take an action, whether to take a break or to go forward, right? That's a self-driving car. And this first attempt actually failed in 2004. And then it took, somewhere around 10 years to go towards a prototype from this vision. And this was done by Google. successfully, in the recent past. So, something like this, was thought about a long time ago, and it took 10 years, and people are just realizing, hey, we need something like this for networking, and that's what's called as the self-driving network. And so the key question is, what does it take to realize something like this, right? As with a self-driving car, you need three things to happen, right? You need to constantly look at the road. You need to constantly, you need to constantly look at the road and collect information about the road. And say, okay, is it a pedestrian? Is it a dog? Is it a stop sign? Is it like a, lane change, divider, right? You need to constantly look for information. And that's kind of similar to what you have to do in the network as well. You have to constantly collect measurements, which is called as telemetry, right? The remote information that you're constantly collecting from the network has to be obtained, right? So that's the first leg that needs to be there. And this is what, all the measurement people are focusing for a while now in terms of, coming up with the entity relationships. And then once you have the data, you need to understand the data, right? You need to say whether it's a, person walking, or is it a dog, or is it a stop sign, or is it just a shadow, right? You don't have to brake in that case. So you need to do some inference based on the data, right? So similarly in networking, you have to, look at the data and say, is there a DDoS attack? Is there a congestion event? Is there, some performance failure? And, you're welcome to use any sort of statistical technique or AI machine learning technique, right, to infer what's going on in terms of the problems. So you have the data, you have the problems which are inferred. Now you have to control the problems, right? Let's say you reroute the bad traffic in a different location such that you provide some isolation for users, or you drop the packets, right? All those are good actions that you can do so that you can take care of the problem that is being identified, right? And once this leg of the puzzle is also here, you need to put all the three pieces together. You constantly measure the state of the network. You infer if there is a problem. If there is a problem, go take an action about the problem. And once you take an action, how do you make sure the problem is gone, or if the problem is still there? You again measure, right? So you just have to go around in a closed loop of this constant measure, infer, control to realize something like a self-driving network. And people have been making great progress in all these different aspects, but in isolation, right? There is a whole bunch of measurement research. There is a whole bunch of recent uptick in internet data science efforts that are looking at the inference problem. And then people have looked at things like SDN and traffic engineering for a very long time now, right? Now it's just networking area is so exciting at this point that it's time to put all the pieces together, because these have been developed for a very long time. Now is the time to do something like this, right? This is like building a rocket. You have all the different equipment. Now let's basically test it by putting all the pieces together. And so that's kind of is a main focus of what's going on in many of the efforts that are out there. So given that I did not touch upon telemetry for a while, I'm going to briefly talk about that, and then I'm going to briefly talk about some of the AI machine learning, given the lack of background in the room, and then go into some of the grand challenges in putting self-driving networks together. But before that, do we have any questions in the room? All right. Okay, so telemetry is pretty straightforward, right? So you have your application running somewhere, let's say a server hosting a website. So the idea of this is, this application is used by a user or is used by some other service. Now, the user can basically launch a bunch of queries into the network. And ask questions like, hey, why am I experiencing congestion? Why am I experiencing DDoS? Or if you're watching a video, you might simply see that, circle of death spinning in your particular screen, and you're like, okay, what's happening? Is my modem down, or is there a congestion elsewhere, right? So all those are different queries that could be run in a query engine, which is at the telemetry endpoint. So this is the starting point of interaction for your web server. So the queries go, and then they collect information from different parts of the network. Let's say there is a switch, there is this control action. They collect information. There are all these line cards in the network elements, like switches and routers. They all have different information. Those all go into the collector. They are stored in the database, and then the data is given back to the application so that the application can infer itself in terms of what is going on. So this is a simple telemetry framework where the application is asking a question and it is getting the data back. So that's just the first step of the process. Once you have that, now go for essentially the inference part. Meaning you can take one or two ways at this problem. You can either apply simple rules, like if there is 50% of traffic overflow, then potentially it's a congestion. If there is 80% of traffic overflow, then essentially it's a DDoS, right? You can apply such if-else rules to identify problems. And the key reason why people do this is pretty straightforward to understand. And even if something changes in the network, it's easy to reason about this, right? It's easy to predict and refine your rules in an ongoing basis. But it also has a whole bunch of cons, meaning it's really hard to develop rule for every single thing that you're doing in the network. And when the network grows really big, it's really hard to scale all the number of rules that you might want to apply for each one of the networking elements. So that's why people go for this other direction, machine learning, which is really creative in figuring things out by looking at a whole bunch of examples and counterexamples. And because of those examples and counterexamples, it can learn a whole bunch of complex behavior as well, right? While these are better compared to some of the problems that you have, they still have their own problems. You cannot reason about what a machine learning model is thinking, right? It might take a decision and you don't know why that decision is valid, or you cannot reason about why that conclusion even makes sense in terms of a particular inference. It might say, hey, here is a DDoS, but it won't explain why it is a DDoS, right? So that's a big problem. Unless you cannot reason about it, you won't take the reasoning in a fair fashion. And it's really hard to know what it has learned and what it has not learned. And so this refining process is also hard, right? Only after taking an action, you'll be able to refine what's going on. Okay, so given this background about telemetry and inference, let's revisit this whole notion of self-driving network. So you have your software-defined networking, which is the control part. Now the grand challenges arise when you want to integrate the SDNs, which are used for taking control and action, with the telemetry as well as the AI, machine learning, or inference component. We just don't know answer to the question like, okay, how do we go about integrating these things together? And even if we can figure out something like that, how do we accommodate what an operator wants, right? An operator might look at the data and he or she will be able to decide what's going on in the network. But because of the fact that your machine learning model cannot be used to explain what it knows, or your rule-based systems are hard to manage at scale, how do you accommodate an operator's intent in terms of what the operator wants to do with the data, right? You cannot accommodate that easily. Now you need to do a whole bunch of accommodation stuff for the operators. And intent-driven networking, that's a new area that is being pushed at to make sure the policies derived by the operators are satisfied by the networks. So that's also part of the picture. And once, let's say you do all the integration, you accommodate the operator's requirements, how do you verify if the actions are correct, right? Your machine learning model might say, hey, I detected a DDoS, and I took this particular action by changing a rule in the switch, and I dropped all these packets. Great. Now, what if you affected a benign user's traffic? How do you verify you just affected a malicious user and not a benign user? Right? Those are all interesting questions that are sitting at the table, and that's why I'm saying this area of self-driving networks and doing internet data science is really exciting area at this point because of some of the grand challenges that are ahead. Right? Anytime you talk to a researcher and gave them a whole bunch of problems, it's like more exciting for them rather than having a bunch of solutions. Right? So that's why this area is like super cool at this point. Okay, so that is pretty much all I have for internet data science. So I'm gonna go next into some of the PhD positions and internships in my group. But before that, do we have any questions about what's been covered so far?
Maybe if nobody asks, I'm very curious. I have one question.
Sure, please.
I'm just trying to understand from like a research and like a very practical thing. So it looks like more a B2B problem, right? It's not coming to the customer. Like who are like big players and who want this problem to be solved, or like how do we think about like
Right.
who?
So that's a great question. Definitely, this is not going towards the customers, right? But the customers are going to be impacted by this. And where exactly these solutions run are in the enterprise networks. So if you think about internet, right, it is composed of a whole bunch of networks connected together. That's why it's called network of networks, right? Now, what we are presenting here is a solution for a specific network, right? All the intra stuff that happens within the network in terms of management, in terms of data collection, in terms of inference, everything is within an enterprise network. Now, when you put all such individual enterprise networks together and connect everything together, that becomes something for the internet. But you're definitely right. This is not for customers. This is for players like AT&T when they're managing their own network, or this is for Vodafone, Reliance, any ISP who manages their own autonomous system. They cannot, go change others' network, but as long as they have control, they can do all this.
Yeah, thank you.
Great. Other questions? Okay. If not, I'm gonna quickly, touch on, something that is of interest to the students based on the survey that we conducted,
Excuse me,
which is
there is a question in chat. I just want to read
sure,
out, not want to miss.
sure, yes.
How does internet data science scale with respect to big data?
This question is kind of like, what is the definition of scale here? Could you explain, Aishwarya? Are you
Like
asking if
base.
the data increases, how does some of these techniques still hold?
Yes, yes.
Right. So I think, I mean, the big data, the petabyte of data that we have been talking about, they're all, pretty much the same, right? I mean, anytime when you read a whole bunch of, articles, these are called buzzwords. So, big data people, when you talk to them, end of the day, they are, looking at petabytes of traffic. And when you talk to networking researchers, they don't call it big data, they just call it data. Uh, and it's again in the order of petabytes of traffic. And a company like Akamai, for example, collects, I would say, exabytes of data, and they have to throw out the data every 10 or so days because that is how much they can hold at any point of time, and that's big data for you, right? So all these techniques definitely are going in that direction. But at this point, what we are playing with is a sandboxed version of these techniques, meaning we collect something from a campus like UFO, which is in the order of petabytes, not exabytes. So we don't know if these techniques will be quickly applicable to something of that scale. But certainly that's again another interesting question that you're asking, right? In terms of scale, I developed something for a sandbox. Now, how do I take it to the big league, right? You're playing a gully cricket, and now you want to go play World Cup. Will the player can do justice in terms of that, gully cricket versus World Cup? That's the kind of question. I think that's a great question. Again, if you're interested in PhD, I'm happy to hire you and work on this question with you. Um, all right. Other questions?
Yes, sir. Thank you, sir.
Of course. Okay. Given we have 5 more minutes, I'm gonna quickly touch upon the aspect that is of interest to some of you. So yes, we are looking for PhD students all the time. We are looking for interns all the time. And so this is how it works, right? So if you are a prospective PhD student, so I would suggest you to go look at this particular link. We do, Oregon Networking Research Group, so ONRG, GitLab.io, prospective. And in that, you have enough information about what is needed of you and what do we offer. And, two things that is always of concern to students is, will my tuition be covered? Will I get funding? Yes, you'll get funding if you join my PhD group. Will I get a stipend? Yes, you will get a stipend too, and that's totally sufficient enough for you to do your PhD. But if you ask me a question like, hey, do I have a chance of getting accepted? I cannot say that because it's all decided by a committee. Of course, I see your application when you put my name on the application, but that decision is entirely taken by a different committee. So I cannot talk to your chances in terms of getting an admit. But definitely go take a look at this particular website. And if there are questions, definitely reach out to me. But the key thing you need to have is the motivation to work on research and motivation to work on these problems. If any of the research topics that we spoke about is of interest to you, do reach out. I'm happy to talk to you one-on-one or as a group, and take it further. So that's a long-term thing. Again, think wisely, think about your advisor well. And I've also answered some of the questions here because there is always a tendency for students to always apply for top 10. Of course, UFO is not top 10. Let me be very frank. But then we all publish in the same places, right? The university ranking is all bogus, and there are so many factors that go into coming up with ranks. Like all the admin stuff, and some universities they just don't do it, and that's why their ranking is really bad. But we all do great research. In fact, some of us do better research than some of these top schools. I, for example, have 3 million funding this year, whereas if you go to some of the top schools, they might have 500,000. And we publish in places like NSDI, SICOM, whatnot. These are the cream of the crop conferences for networking, and our students, they all go for companies like Snapchat, Google, whatnot. So do take a look at that, and if you're interested, reach out. I'm happy to entertain. There's also a short-term thing going on, and I really wish a CEG student or a set of students took part in this. So we offer summer internships, and this is paid. You will get a stipend, your flight will be covered. All that is needed from you is to work on cool research with us. So that's a good place to be in. You work on a problem of interest to you, and you get paid, and you get paid well. So that's another opportunity. So we did this for 2 years before pandemic, and the funny thing is, I sent a note to a whole bunch of CEG professors. I don't know if it was forwarded to you guys. So I'll stop there. I don't want to go further into that. But students from SSN were pretty receptive, and we were hosting students for 2 years, and they did fantastic work. We published with them. Many of them got good recommendation letters. Some of them decided to, come back to us for PhD. Some of them also went for good jobs, and we wrote good letters for them. So if you're interested in summer internships, do apply or reach out to me. I'm happy to, um, please reach out. And again, you should definitely, spread this word to your friends who are not here. It's not just, you have to keep this information to yourself. Definitely, spread to people, because the more you spread, the better CGNs, grow as a community, and that's super important. All right, so that is pretty much all I have, and I'm going to stop here and see if there are any questions with respect to anything, right? Talk about research, or if you want to talk about, these positions, both short term and long term, or if you want to talk about, grad school in general. I'm here for the next 5 or so minutes, and I'm happy to answer questions. Thanks.
That I'll also stop recording so we can have nice discussion.